sure it's like weeks. I was trying to argue about money, and he says like, so we need to like,
tell all it's okay to call on Monday.
Call
like the police.
Yeah.
Is it possible to do over the weekend? If it is,
they might be open. Yeah.
Yeah, because I was thinking the run out just today or something.
Yeah, it's worth calling.
Okay.
We need money like.
Yeah.
Yeah, we have like a new
Turned out,
slideshow.
like,
I can show you really quick. Is it polar like connected? So, you want to just show the polar now? You just separate.
what's it called? Oh,
Oh, we can't. Like this? Oh. Let's see. It's not working. Duplicate the screen. Oh, there we go. Got it. All right, sick.
So for those of you that are here right now, if you could take the time, just go to this poll view and we get to create a nice word cloud. What do you think of when you hear quantum computing? You can, if you.
Sorry.
Yeah, no problem.
Yeah, and feel free to share out loud too if it's like lengthy response.
There's also like a QR code.
Move whichever was easier.
It's pretty small. There we go. As we wait for people to come in. Yeah, quantum mechanics. It's a good start.
Right. We are recording.
Oh, there we go.
Okay, no worries. my laptop or anything? Like for speaking or?
I'm probably using.
Okay, I'll just check mine then.
Your thing's not working.
Hmm.
Not true.
Oh, it's because it's dead.
I just
What's it called?
you should get Arch's.
Control from my laptop. That work? Okay, yeah, let's try.
Oh wait, am I doing this? Oh shit.
Oh no, sorry. The name we just copied. So
Okay,
it
okay.
don't actually like listen.
Okay. So I'm gonna be doing this for position and this dot screen.
Okay.
Oh wait, no, no. The front.
Okay.
1 second.
I can do entanglement.
'Cause like, I already
Okay.
and I've done that before.
Lucky. We should have introduced our own. This treasure board.
Time to get started.
Another menu. Give it like one, like a 9 or 2 star. For this workshop, we're gonna be using our laptops, so just be sure to have that out. Yeah, we'll be sending you like links and stuff for Jupyter notebooks to download. So
Tiny bro. We figured it out.
it's a tiny one.
Oh, okay.
They'll just check it.
Awesome. And then I have to give work to
I'm just gonna talk about some things on the word cloud.
Yeah.
Okay. So as people filter in, I'm just gonna talk about some of the stuff you guys do on the word cloud. So obviously the biggest one is physics, quantum computing, very based in physics. It's based in specifically quantum physics, which is the physics of very, very small objects such as electrons, atoms, photons, stuff like that. It's also very into computer science, as quantum computing requires quantum computing algorithms that are derived from computational skills from computer science. So it's kind of like the intersection of quantum physics and computer science. Encryption is also another big one. Quantum computing. I don't know if you guys have just been hearing on the news, but there's all these headlines that's like quantum computing can break the world's encryption in 10 years, 20 years. And yes, there is an algorithm to break the current leading mode of encryption, RSA encryption, in quantum computing. But obviously our hardware right now for quantum computing is not up to par and cannot run that algorithm at the efficiency required for it to be dangerous to encryption as a whole today. And yeah, so I see people writing fast and rapid, and quantum computing is not going to be faster than classical computing at everything. It's going to be faster at a very generalized subset of problems that computer science will be a lot slower at. If you guys have heard of P and NP hard problems, there is some problems which require specific computation that the properties of quantum computing are going to aid in a lot more than normal classical computer science would. And we'll explain that all in the slideshow that I'm about to show you guys. And I think that's a good summary. Yeah, I think that's a good summary of what you guys wrote down. And do you guys have anything else you want to say about quantum computing that you've heard about, read about in the news? Awesome. Like to hear that.
We'll move on.
All right, just pull up the slideshow. That's the first one.
All right, we just did
Okay,
this.
yeah. So welcome to our Introduction to Quantum Computing workshop. So we are Quantum Computing Club at UNC, and we're the first quantum computing club here. My name is Saki Mala, and I'm co-president.
My name is Advaith, and I'm also the co-president.
And my name is Sakshi Mustad.
Okay. So this is just an overview of what we're going to be covering. So first it's going to be the introduction. So what is quantum computing, and going to a little more to theoretical principles like superposition and entanglement that kind of build its foundations. And then we're going to be coding on IBMQ using a file that will be sent to all of you guys. And then some wrap up and remarks.
So what is quantum computing and why is it so important compared to classical computing? So the idea in classical computing, speed is governed by these things called transistors. Each transistor can do one calculation, one bitwise calculation for a computer, right? And right now we're creating transistors that are slowly getting smaller and smaller. I think currently the world's smallest transistor is about like 3 nanometers in length. And at one point, we're not going to be able to make these transistors any smaller. And that's where quantum computing is going to step in and try to speed up the actual process of computation in itself in order for this limitation of transistor size to not affect the computation. So improvements in classical computing are going to be slowing down. Advances in hardware are going to be harder to find, especially with our transistors. And quantum processing is going to change everything. And as you can see, the quantum computing software market size is actually steadily, exponentially growing. Well, these are some projections. Well, it's been growing for the last couple of years, especially in North America. And it's going to continue growing. And we're trying to get in at the base level of that and show people the new and exciting world of quantum computing.
So what is quantum computing? So basically it runs on something called qubits. So as we were talking about earlier, bits are binary digits and qubits are simply quantum bits, meaning they can be in a state 0 or 1, just like a normal bit, but they can also be in a superposition state, which is something we'll discuss later. But basically, they can be in a state kind of that's in between 0 and 1. And that picture kind of shows a visual, like an artistic representation of a qubit, but we'll get into like the actual like diagram. Quantum computers can also possess different structures. So like these qubits can take many different forms. They can be in a superconducting chip that IBM uses. They could be various ions. So there's like something called trapped ion quantum computing, where individual ions are the qubits. Or you can do photonic quantum computing, where the polarization of light is the qubit. There's also neutral atoms, where the neutral atoms are qubits. But basically anything that's really, really small and can have a quantum state can be a qubit. The last thing is quantum computers are never going to replace classical computers. Quantum computers work with classical computers. So as we were talking about earlier, quantum computers can only solve a small subset of problems, like for optimization and other related problems. But they're actually not very good at just straight like math, like addition and multiplication. But they do possess really unique qualities to help in other problems. Yeah, so they won't replace normal computers. They'll work with them.
Okay, so we keep talking about this thing called a qubit, but what is a qubit? So a qubit is the basic unit of information for a quantum computer. It stands for quantum binary digit. Qubit. So right here, this is an example of a bit. A bit can be either 1 or 0. Straightforward enough. A quantum bit can still be 1, can still be 0, but now it's a sphere and it can be anything in between. So these arrows point to different states of a qubit. This red arrow would be the 0 state of a qubit, which is just like a classical bit can have a 0 bit. That would be the equal bit in quantum. We also have a 1 bit, And now we can also be exactly equidistant from 0 and 1. We can have a state that's right in between 0 and 1 in something called superposition, which we're going to talk about in the next few slides. And the idea is that a quantum bit can be in any one of these states. Any point on this sphere, on this unit sphere, can be represented by a qubit, right? We talked about some of the physical structures of qubits: trapped ion qubits, superconducting qubits, neutral atom qubits, photonic qubits. You don't need to know exactly how all of them work, just that they all follow the same basic principle of a qubit being represented by a sphere.
So superposition is a truly mind-boggling concept in the world of quantum computing. So it's one of the key principles that sets quantum bits or qubits apart from classical bits, and it's essential to grasp how it works to fully understand the power of quantum computing. So what exactly is superposition? Imagine a classical bit like the light switch in your room. So it can be either on, which is 1, or off, 0. It's kind of like a coin that can only be heads or tails. And that's classical computing in a nutshell. But in quantum computing, we deal with qubits, which, as Saksham said, and they're nothing like classical bits. So qubits are kind of like magical coins that are constantly spinning, and they can be in multiple states at the same time. So they can be 0, 1, or anything in between. And that's what we mean when we say superposition. So it's kind of like a light switch that so a classical bit is kind of like a light switch where you just kind of flick it on or off, but a qubit is kind of like one of those light switches where you can move and like change the brightness if you want to kind of visualize it. And so now you're probably thinking, why does this matter? Or why is it useful? So that's where the magic of quantum computing comes into play. So because qubits can exist in superposition, quantum computers can perform operations on multiple numbers with multiple possibilities simultaneously. So if you have a complex problem with countless variables, kind of like searching through a massive database or factoring a large number into prime factors, classical computers would need to process this step by step, and this can be incredibly time consuming. But quantum computers, thanks to this principle, can explore all these possibilities simultaneously. And this dramatically speeds up the process. And this is just one of the many problems that quantum computing can help tackle. And as we said, this is kind of a field that's like still in the making. So scientists and like researchers and computer scientists, especially that work with theory, are trying to come up with these problems that quantum computers can solve more effectively than a classical computer. Because obviously, as Advent said, quantum computers cannot replace classical computers by any means, but there are certain problems that classical computers are like simply just not equipped to tackle.
Okay, so measurement. You guys have been hearing about superposition and how great it is, and it sounds like there's just an infinite number of states that this qubit can be in. But in actuality, we can't actually see the qubit in any of these states. A qubit can be in superposition, but as soon as we see the qubit, as soon as we look at it, or the technical term is to measure this qubit, it's going to choose the state 0 or 1. So we have to actually use quantum computing to manipulate these qubits while they're in the superposition states, but we can't actually measure what value this qubit is in the superposition state. As soon as we look at it, it's going to choose 0 or 1. If our qubit has a vector that's directly between 0 and 1,
This is just like the vector that shows the superposition state.
yeah, so this is 0, this is 1. So if we have a vector at exactly 0, when we measure it, we're always going to get 0. But if you have a vector that's right in between 0 and 1, like exactly halfway between, we're going to see 0 half of the time and 1 half of the time when we measure it. Now this might not seem super useful. You might be like, okay, so it's just going to give us a random value, 0 or 1. But what we can do is put these qubits into the superposition states, use quantum computation, and then in the end, it's going to end up resulting in 0 or 1, and that's the result we're going to end up using. Another thing we can do is something called shots, or we run a quantum circuit multiple times, and that's going to give us a good estimate of the probability value. So let's say we have like a qubit that's directly in between, and we run this circuit 1,000 times. We're going to get 0 about 50% of the time and 1 about 50% of the time. And these are some of the ways that we can use measurement to help in quantum computation. Just another example, this vector right here, that's a lot closer to 1. When we measure it, we're going to get a lot more 1s than we are 0s. And we'll be able to distinctly discern whether it's like equal superposition or unequal superposition, or if it's in a state like 0 or 1.
So this is kind of like a thought experiment. So you drop your phone, and then the split second as you drop it, or as it crashes the ground, you don't know if it's going to be cracked or not. So it's kind of in a state of superposition, and it's not until you pick it up where you measure it, technically, that you know for sure if it is cracked or not. So it's kind of just to visualize things with the day-to-day.
Okay. So this is just making sure you all understand. If we're in a block sphere, if we have some sort of qubit state, right? We can't actually see it in this state. We have to measure it first, and when we measure it, we're either going to get a 0 or a 1. In this case, it's a lot closer to 1, so we're going to get 1 about 85% of the time, and 0 about 15% of the time. And in this case, it's exactly halfway in between 0 and 1 on the x-axis, and this is going to be a 50-50 split between 0 and 1. Yeah.
Why is this a 3-dimensional value rather than a 2-dimensional value?
We can manipulate the qubit in 3 dimensions. So yeah, that's right. As it pertains right now, it's not affecting our 0 and 1, but in some quantum algorithms, we'll be able to manipulate it in 3 dimensions. That helps with the process.
And we'll be getting into like gates, which can help you visualize.
Wait, are there any other questions real quick? Awesome.
Okay, so in the realm of quantum physics, we encountered this remarkable phenomenon called quantum entanglement. So this concept was once described by Albert Einstein as spooky action at a distance. And this reveals the connection between particles, and this is completely independent of the physical space that separates them. So quantum entanglement occurs when particles become correlated in a way that defies all classical intuition. So the state of one particle is instantly influenced by the state of another, regardless of how much distance there is between them. So kind of like how a particle in the sun could be like entangled with something like a part of your body. And this instantaneous correlation is this fundamental feature of quantum entanglement. So imagine two particles, each with equal and opposite values. So kind of like the spin of electrons. And when these particles become entangled, even if they are separated by light years distance, it seems that it is irrelevant in the realm of quantum entanglement. And this concept of entanglement was actually introduced in the EPR paper, where it demonstrated that when you measure a property of one particle, you instantaneously know the particle or the property of the other. And this challenged like classical notions and hinted at the existence of these hidden variables. But future experiments and developments in quantum physics reveal that these hidden variables that Einstein described in his theory was incorrect. So quantum mechanics emerged as a result of this as the correct framework to describe these. And it showed that particles can indeed be entangled and that their states are correlated instantaneously. So this is irrespective of the distance, which is a phenomenon known as non-locality. And beyond its theoretical implications, quantum entanglement obviously also has practical applications. So it underpins things such as quantum cryptography, which I know a lot of people mentioned in the word cloud, and then also quantum computing.
Does this allow us to transmit information faster than the speed of light, or?
Not actually, because when you entangle particles, they have to be in close and like right next to each other. And, like for example, photons, they have to interact with each other to be entangled. And then when you bring these particles away, that requires movement at less than the speed of light. So that therefore you can't transmit information. So yeah, it doesn't break physics.
Yeah.
Sorry.
That's a good question.
Yeah.
But unfortunately, no teleportation.
Also, sorry, it's worth noting that when you have two entangled qubits, you can't actually represent them with a block sphere. Because a block sphere is for one singular qubit. So when you have two entangled qubits, like there's no like really good like visual for that. So when you think of a block sphere, think of just one singular qubit. For entangled qubits, it's technically like two separate like quantum particles that just can't be described by one like diagram. Yeah.
Okay, so now we understood what a qubit is. Now how do we change it to that? we're gonna do something called gates, okay? And these gates are gonna help us change the state of qubits in a specific way that allows these qubits to complete a useful task. This is the idea of quantum computation. It all relies on these gates. And the gates are gonna be on the next slide. Yes. Okay, so these are three of the most basic gates. Okay, we have the Hadamard gate, the Poly X gate, and the Poly Z gate. These are just names, they don't mean anything. I think the simplest gate is the Poly X gate. It's pretty much like a NOT gate in normal binary. It rotates around the x-axis, which is right here, 180 degrees. So that means that if we start at 0, we're going to end up at 1. And if we start at 1, we're going to end up at
0.
Yeah, awesome. Okay, pretty straightforward. So this is another really straightforward one is the Poly Z gate. It's going to rotate 180 degrees around the z-axis. So that means that if we start at 0, we're going to end up at
1.
no
0.
0. Trick question. Yeah, so this is the z-axis, right? So if you rotate 180 degrees around the z-axis from 0, it just ends up at 0. And if you rotate 180 degrees around the z-axis at 1, 1. Okay, yes, you guys are getting it. Yeah, those are the straightforward gates. And now we come to this gate. So far, we haven't even talked about superposition yet. But this gate, all I can think of it is it creates superposition. Specifically, it's going to create equal superposition. It's the simplest gate that creates superposition. It's going to start at 0, and it's going to come down right to the midpoint between 0 and 1 in the positive direction of the x-axis. And since it's the positive direction of the x-axis, we actually give it its own name. We give it its own name. We just call it the plus state. And if we did the same thing from 1, it's going to rotate back, and it's going to go exactly 50-50 between 0 and 1 in the negative direction of the x-axis. So we can just give that a name called the minus state. So these are the 4 main states of quantum computing. There's also a different name for the plus state of y and the minus state of y. But for today's intents and purposes, we don't need to cover that. Yeah?
If there's a poly X and poly Z gate, why isn't there like is there a Y gate?
Yeah. Yes, there's exactly. There is a poly Y gate, but I just didn't cover it because it for today's demonstration, it effectively covers the same uses as the X gate. Because if you imagine we wrote 180 degrees around the Y gate, it's going to go from 0 to 1 and then from 1 to 0. But that's a good question.
Also, for the y-axis, it's also called the imaginary axis. It's where like imaginary numbers come in from quantum physics to quantum computing. That's what it also allows for speed up the quantum.
Yeah,
And-
it gives a, oh, go on.
Just what happens if you use the Hadamard gate on something that is not on Z, X, or Y?
Okay, so then, you can use the Hadamard gate that's from not on X and Z, and it's gonna almost perform like the same rotation. It's gonna go somewhere different, and it's explained. All these gates can be explained by matrices and like vector notation, and what quantum computations do is they're gonna multiply these vectors and matrices, and that's how they get the final state of the qubit. You wouldn't be able to explain it using intuition. It's just only if it starts from 0, it's gonna go to the plus state. And also, if we start at the plus state, it's gonna go back to 0. So, it completes like a circle right around here. Does that make sense? Awesome. Yeah, if we started somewhere else, it's gonna like end up like here. It's gonna complete like the same motion.
It follows like the same like rotation like the angle on both axes.
Yeah. Yep. Sounds good.
We just covered this.
Yeah.
It's just to kind of show everyone what the visual looks like.
Yeah, just a little bit bigger. And this is the Z gate. And if you start at 0, it's gonna end up at 0. Okay. Awesome. Okay, so we're gonna play a fun game to demonstrate the
Let me
properties of
focus.
superposition and measurement. It's quantum tic-tac-toe. So right, let me come on board. I'm also gonna pull it up on the laptop. Just so you guys don't get too tired of listening to us talk. Oh, wrong computer.
Me and Sachin will demonstrate the game real quick.
So there's a few different levels of superposition, measurement, and entanglement. So we're just going to demonstrate the highest level here and show you some of the properties. Okay. So this is the website. Let me increase the size. So it starts like tic-tac-toe. You have an X and an O. Except you can place an X just like this, or
I can also do an O, just like normal tic-tac-toe.
this is just like normal tic-tac-toe. Or I can do something like this. So now the X is in superposition. This X is in superposition. It can either end up here or here. So it's a 50%, it's an equal superposition. And 50% of the time the X will end up here, and 50% of the time the X will end up here.
I'll demonstrate that with O. We can do it across two different squares.
Okay, and then now to demonstrate the property of measurement, what we can do is actually measure one of these qubits, or the X or the O. If I press and hold on this X, I can actually measure it, and it'll automatically decide 0 or 1, or in this case, this square or this square. And in this case, completely randomly, it decided this square. Another thing that you can do is you can entangle with another qubit. So you see this X up here in the top left? I can actually drag an empty square as O's turn to the X. And now the O is entangled with the X. So 50% of the time, this will be O and this will be X. And the other 50% of the time, this will be X and this will be O. So that's demonstrating the property of entanglement. So this game, I thought it was fun. It's actually really difficult to get really good at it. And it demonstrates the properties of superposition, measurement, and entanglement.
Also, if you fill out all the squares, it'll measure all like the superposition and entanglement squares automatically. So
Yeah.
like if you do this,
If you fill out all the squares, it automatically measures every single qubit on the screen at the moment. So in this case, it ended up like this, and it's X's turn, and this is definitely a draw. If I just play here.
no.
Oh.
Oh, it randomly chose. Okay.
Well, yeah. Oh,
Based on the time, I would have won.
yeah. Actually, yeah. It's a good point. Okay, you guys like find a partner.
Yeah.
Yeah.
Find like people to play with.
Yo, I need some help. Oh, no, we got it. No, we got it. You need help. Yeah, get shit up. Yeah, I've been to some of the club. What the
And then we're gonna have a tournament, and then tic-tac-toe, and there's actually also fun chess, which I feel like that's a lot more. We should add it to sixth grade, so that the rockets, to see. Yeah, regular chess, yeah, and then we're also. Have a worksheet.
How does that work?
Yeah, this one's actually gonna be about one word key, so.
How do you win?
I think it's like a lot.
I won that one. Double tic-tac-toe, really? Double tic-tac-toe? How? I got notes.
What? A developing theory that's trying to.
Oh, yeah.
To make it more secure. Yeah.
How do you win?
Yeah. So you just want to like 30 minutes before the event, 30 minutes after, make sure it's. That's basically it, but you'll be like participating.
Okay.
Yeah.
Oh, you have to do two.
Stop taking my name.
You went. Seriously, just put an X on the top.
Well, like, that's not how it works. Last time.
There's just a limitation. And is this actually relative? Or just saying it?
Just a fun way to demonstrate that. Time that's O. This revision is half the time that's X.
Oh, yeah.
It doesn't actually use quantum, it's not actually using a quantum computer, but it's just simulating the property. So like, this is superposition, this is measurement. Like if I tap and hold, this is measurement, and then I can do like, this is entanglement. So that's the idea. Yeah, and in a few minutes, we're gonna start coding actual quantum computers. So
I feel like that's more straightforward than quantum detector.
coding the quantum computer, yeah, there's a difficulty curve.
Yeah.
Like, it makes a superposition from 50 squared.
Okay, wrap up your games in 1 minute. We're gonna get to the front of the workshop, the coding. Yeah, we're gonna code on a real quantum computer, everyone. So yeah, get excited.
Yes, sir, let's go,
Yeah.
Wait, let me change.
Bro, you win this, right? Well, this was. Oh, yeah, I win. But this was stupid. I hate quantum detector.
So I can,
I'm gonna write that.
Wait, I'm gonna change the color of this.
yeah. What is it? 3A2 per 9.
Bro, no.
Hey. Okay, for those of you that have a computer, this tiny URL will direct you to a Jupyter notebook where you can download, yeah, the code you're gonna run on a quantum computer.
So just.
Yeah, just download it, and we'll show you where to export it in a few minutes.
Yes.
What are the practical applications of quantum computer?
Oh,
What's your frame of reference? If it's down 90,
that's the normal, right?
what determines which way?
So how does that change? How does the
If you start at the top of the sphere, why can't you just rotate the sphere?
What kind of code is that? Let's say you can't just rotate or like.
What's your?
It's normal thing in our class, it's not like an actual.
So what's the point of going down to the over? Just go over. Like why do you start down?
It's a
Instead of just going.
fortified, all the qubits, in order to do its fortified
45 degree radius. So you guys, okay, 45 degree.
So that's how it works.
It's like, they're like, because it's, that's why,
Did you end up in the same position? I need to finish that part.
you mean like, why is it radius?
Like,
Yeah, like, for example, because of the rotations that are.
and why it's going like, if you're putting up a bunch of these outcomes in superposition, and then which is most likely. I wonder if that makes sense. Yeah, well, if you come Monday, I'll.
Okay, so for coding, we're gonna use a Jupyter notebook and we're gonna run it on something called IBM Quantum Lab. So the first step is you wanna go to this link right here and just download the IPYNB file.
Do we just run it on Colab? Or?
No, it's not gonna have the libraries required for running this. So we're gonna have to run it on IBM Quantum Lab.
We'll show you how to create an account on the next slide. It
Yeah.
should be really simple, and that's where you'll import all the notebooks into.
Yeah, so as soon as everyone's done with this link, wait, is the link on the board?
Yeah.
Okay, so you want to go to quantum-computing.ibm.com/lab, and you want to click here and create an IBM ID account, because I'm guessing none of you guys have an IBM ID account.
I do.
Oh, he does. But the rest of you guys need to create an IBM ID account for IBM Quantum Lab.
We will need help. Maybe the website. You guys go to the website.
Isn't it safe in the position? Go for it. So what about our development?
Yeah, you know, actually, this is
starting.
but just keep it downloaded, we're gonna import it into like this idea.
Alright.
Yeah.
Whoa, he's really cool guy.
And do we have to worry about any for license agreement at all?
You have to accept that we use the website.
Is it just a tutorial? Oh, right.
Oh, yeah, yeah. Yeah.
Yeah. So the next step is
All right, create an IBM ID. You're gonna fill out all the information it asks you. You're gonna end up on this screen. You want to click Launch Lab. If you don't see this screen, just go back after you sign up. Just go back to the link at the beginning. Okay. And then you're gonna end up at this screen over here. Who is anyone not at the screen? Yeah.
okay. Yeah, no worries. Yeah, if any of you guys need like a few minutes, just don't be afraid to let us know.
Okay, I'm sorry, what, here?
Just go back to the just do slash lab.
Oh, it's slash. Yeah, it just redirects you to a new site after the year.
I already have.
Okay, if you're not on the website after making an account, just go back to this link, and it should take you to this website. And once you're on this website, you want to upload the file.
That's the tiny URL file.
Yeah, this is the link.
Yeah. Their ID, so you should. Okay. Yeah. Yeah, and.
Okay.
Oh, no, no, no. This is, but, should be open assumption. Do you need to just edit? Yeah, okay, so you need to add that. There should be some other percentage for. Yeah, yeah, actually, yeah. Push the thing out. Yeah, it should be whole.
Are you guys, is this your first time at HackNC?
No, it's not.
Oh, are you guys a team? Oh.
No,
You got there.
Oh, yeah, you got this.
Unfortunately.
Yeah.
Yeah, my first, last year at HackNC, all I did was, me and my friends coded a 2048 for like stats. We were bored, but we just simply tried.
That's a fun game. Dude, I remember when 2048 was so popular.
Also, like, I feel like at least for HackNC, like you can literally just create like a Spotify,
Yeah.
and you'll win something, and it's like
There's
it's
so
not
many
that hard.
prizes,
Yeah.
especially if you like do one of the ones that like says like use this specific program.
Yeah. Then like only like 3
Yeah,
teams,
yeah.
4 teams are gonna do it. How many people? Do you know how many people registered this year for HackNC?
I believe my because his friend runs. Or is part of it. Okay. Is everyone on the screen? Has everyone uploaded? Who has not uploaded the file?
All right.
That's awesome.
Oh yeah, that's the same file. Okay.
Okay, so really quickly, for those of you that don't know Python, we're going to be using a Python library called Qiskit. So what is a library? It's kind of like, you can think of libraries in Python like apps on your phone. Each library is developed to help with a very specific task, just like these libraries here. So like Google Maps can help you find your house. Text messages can help you send messages to friends. Qiskit is going to let you interface with a quantum computer and simulate quantum computers. Yeah.
Oh, sorry.
Once you log in.
So what we're gonna do in the coding section is we're gonna create a circuit in Qiskit. And there are 3 steps to making a circuit. 1, create an empty circuit. 2, add gates to the circuit. And 3, run the circuit.
Let's go to the yeah. Oh, do you want me to go to the next one?
Okay. Just like adding ornaments to a Christmas tree, we're gonna get our empty Christmas tree, our empty circuit. We're gonna put ornaments on it. It's exciting, just like Christmas. Okay.
Okay.
So step 1, we need to create an empty circuit. So in your first block, you want to write down this piece of code. QC is just going to be the name of our circuit. So we're just calling it QC, stands for quantum circuit. You can call it whatever you want. QC equals, and then quantum circuit is going to be a function to create a quantum circuit object. And it's going to take 2 parameters. The first parameter is going to be the number of qubits. I probably should have wrote that down. But yeah, this parameter is going to be the number of qubits. So we're going to create a quantum circuit with just 1 qubit. And then the second parameter is going to be the number of classical bits. So if you remember, when we measure a qubit, it's going to end up at either 0 or 1. So to record what happens when we measure a qubit, we need a classical bit. So what's going to happen later is we're going to have our qubit, and then we're going to measure it, and we're going to send that data to the classical bit. So that's why we have 1 quantum bit and 1 classical bit in our parameters. Any questions? Awesome. Do you have a question?
I was thinking, and wouldn't be able to make quantum circuit with say 2 quantum bit and 1 regular bit if we only needed the 1 regular bit for our output, but
Yeah.
Okay.
Yeah, no. Yeah, so all we need is that 1 classical bit to store our output. We can have 5 qubits, we can do a calculation and then store the result in 1 classical bit. Or if we needed like a binary string, if we needed like a number that needed like 5 classical bits to hold a value, we could have 5 classical bits and hold values of like 5 different operations. this is just the framework to make any sort of quantum circuits. Number of quantum bits and number of classical bits. So,
Oh, yeah. Question. Not like multiple bit to one bit or like.
what will happen is when we measure our qubit, we're like doing an operation on it. So it's going to give us 0 or 1. And then we're just taking that value and we're storing it in the classical bit. Let's say now I stored a value in the classical bit. Now let's say I get another qubit, right? I do some operations, but then I store the value in the classical bit. It's just going to overwrite whatever was there. Yeah.
So ideally, if you're using all the qubits, then you want to have equal number of classical bits. Yeah, that's. And in some cases, you would have like what's called ancillary qubits. Basically, you're just using the computation, but you don't need their output. You don't need.
Okay, so yeah, so everybody should have written that piece of code in the first block. Let me also do that.
Yeah, if
real
you guys
quick.
are getting any errors too, just fear, like let us know. A lot of the times it's like syntax.
Okay.
Capitals.
So really quickly, the first thing you want to do is run this very first block. This is going to import all of your libraries. And at the end of that, it should say libraries imported successfully, just like mine does. You want to run that first block. And then in the second block, we're going to create our quantum circuit. Ta-da! Okay. Any questions? Awesome. Okay. Next step. Step 2 is adding gates to our circuit. Now we can add gates to our circuit. So the way we're going to add a gate is we're going to have the name of our quantum circuit. You want to use whatever you called your quantum circuit in the first line. In our case, our name is QC, so we have QC. We want to do dot and then the name of the gate you want to add. So Hadamard gate is going to be an H, Z gate is going to be a Z, and the poly X gate is going to be an X. And in the parameter of this function, it's going to be the index of the qubit you want to add the gate to. 0 means the first qubit in your circuit. So computers just start counting at 0. So if you want to put the gate on the very first qubit in our circuit, we want to have the parameter 0. Since we only have one qubit in our circuit, you guys are all going to have the parameter 0 in the function as well. So let's go back and fill out the piece of code. So this block is asking you to add 2 X gates to your circuit. So the way we're going to do that is QC.X and then QC.X, just like that.
Why are you doing QC.X 0 2 times?
So the block asks us to add 2 X gates to your circuit. So that's why I did it twice. Yes.
It's good, like 15 minutes.
Yeah. All right. So for the next step, the next step in our quantum circuit is we're gonna. Oh, this is an important note actually. Just whenever we're starting creating a qubit, they always start in the 0 state. So after we put our 2 X gates on it, it's gonna end up back in the 0 state again. Anyways, next step is we're gonna measure our qubit. This is gonna be in the next block. It's gonna be QC.measure, and then it's gonna be 0, 0. The reason it's 0, 0 is because we want to measure the very first qubit, which is the 0th index. And then we want to send that result to the very first classical bit, which is also the 0 index. So in the next block,
Yeah.
the next block, we're going to write QC.measure 0, 0. For those of you that just came in, you missed a lot of explanation. We're gonna post the slides on our group me. So if you guys are interested, after listening to the end of the coding segment,
Yeah.
you guys can join the group me and you can look at the other slides.
We'll have our QR codes for all of our interest forms and Fall Fest event and everything at the end, so.
All right, the next step is draw. So you want to just write qc.draw, pretty straightforward. You're gonna see exactly what this does in a second once we run the code. It's actually right here over here. What's gonna happen in the draw is it's gonna tell you what base you put on it and if you measured it or not. So run your 2 blocks of code now. Run over time.
Oh wait, will this use up our credits on the IBM form?
I don't think it will. This is just drawing everything that you've done. So you have your quantum bit, you put an X date on it, you put another X date on it, and then you measured it and sent the result to your classical bit. This is just the summary of what you've done. Okay.
Yep.
Oh wait, why is there 2 measurements?
Oh, no, there isn't. Is there?
There we go. I fixed it.
Oh.
Okay. So if you want to see what happened to the quantum bit, we're going to do something called visualize transition. So this is one way that we're going to simulate what happened to the quantum bit. Trace equals true is just going to give us a nice little GIF of what happened. It looks pretty cool. And this is the name of our quantum circuit. So we're just going to write this piece of code.
Visualize transition is not defined apparently.
Oh, I spelled it wrong. I spelled it wrong in the lab. Yeah. So just to make sure you guys are paying attention, you have to fix my typo. Yeah, visualize the spell wrong. So you guys have to fix that.
Ooh, wait.
What's wrong?
Mine worked.
It works. Wait, run it again.
With the typo.
With the typo?
Huh?
With the typo? That's
It
cat.
definitely did not work.
Yeah.
No, it did, I promise.
With the typo.
Wait, no, I know, no, it is. It's 1 minus.
Are you spelling
What the fuck?
Oh, it's spelled with
Oh, it's supposed with an S.
yeah. No, it's not. It definitely is not. Oh wait, go back and run everything. I think that might be it. That's
Oh.
probably it. Just go back and run. So it's probably gonna work for them. Let's just run this.
No.
This, what is it?
Just if you only run this,
Mhm.
and then you run visualize transition, you have to run it. Okay. You can't put measure on it, and then visualize the transition. I forgot.
But why is it working for the other people?
It's not.
Oh, it's not?
Okay. Give us. So the issue was after you measure the qubit, it doesn't store the transition anymore. So you actually have to run visualize transition before you run measure. So you guys don't have to do that. We're just gonna show you what it looks like real quick. It takes a few seconds to run. While this is running for us, what you guys should do is run the next block. Yeah. What the next block is gonna do? Go down.
Oh wait, sorry.
Yeah. What these 2 blocks are gonna do is run shots. It's gonna run shots and it's gonna measure our qubit and it's gonna give us a nice output on what 1024 shots are gonna look like. So that's running this circuit 1024 times. So we're gonna run the circuit 1024 times. And what we would expect is 1024 zeros. So run blocks 3 and 4, and it's gonna give you a nice histogram of what the results we got from our qubits.
Why is it taking so long? I like didn't run
It takes a while. I'm just gonna, that's unfortunate. Nice. There we go. It takes a while.
Okay, also,
Yeah.
do you, to get like snacks and stuff, do I need like stickers? I'd be able to get snacks, right?
You should just get food from the.
Is there food?
No.
Not a single snack? Like not even like a little food
Probably
snack?
like water.
Huh?
Wait, I don't know. You can check.
Okay, I'll check. Just cause
Why is it taking so long?
but do I need like my?
Because the Wi-Fi is shit. Bro, the Wi-Fi is so bad. Or my computer is bad.
I don't think it's a Wi-Fi. There's no way. Maybe.
Dude, it's taking. The Wi-Fi is running really slowly, so it's taking like ages for the code to run. Because we're using IBM Quantum Lab. So. Oh, there we go. It ran. Awesome. Okay. So everybody listen up real quick. This is what you're gonna get from your visualized transition if you run it before the measure. And it's gonna go from 0 to 1. This is our first X gate, right? And then if you continue, it's gonna go back to 0, and this is our second X gate. Any questions? Awesome. So what the next pieces of code are going to do is measure this qubit 1024 times, and what we're gonna get is 1024 zeros, and it's gonna plot it on a nice histogram, so we know our result is 0 from this quantum circuit that we created. And we're running out of time, but the next few blocks after that, we'll run this code on an actual IBM quantum computer, but judging by how slow the Wi-Fi is running right now, oh yeah, this is our histogram of 1024 zeros. But yeah, we're gonna repeat this step with an actual IBM quantum computer, which will actually create the circuit and run it 1024 times. But judging by how slow the Wi-Fi is right now, you're probably not gonna get the result as you're sitting here. So if you want, you can finish up the steps in the what's it called? The Jupyter notebook that we gave to you guys, and you'll actually get results from an actual IBM quantum computer. And what we're gonna do now is just go through the conclusion of our slideshow and how you can join our club if you're interested in quantum computing and learning more about how this works.
Okay. Yeah. So this is our workshop series so far. So our first workshop was actually an intro to quantum computing workshop, which is kind of similar to this. And then our last workshop before fall break was advanced quantum circuits. So we just went a little more in depth into that, and also did some more coding on top of this. And then our workshop on Monday actually is going to be about quantum computing architecture. So we're going to be learning about superconductors and ions. And then this is some other workshops. And I think the quantum cryptography algorithms workshop we're probably going to be partnering up with cryptography or club too. So this is just kind of an overview of everything. And quantum error correction is actually like a huge field that's like really in the works right now. Has a lot of potential. So we actually have a quantum fest coming up on November 12th from 12 to 4 p.m. Currently, we have our confirmed location as Union room 3206, but that is subject to change because we're also looking into Citizen as a venue. And then also make sure you join the group meet for the most updated information. Oh yeah, and a huge part of our event is it's IDM and sponsored, so you'll be able to get a certificate participating in the Qiskit demos, but was just attending workshop. And you don't need to have much prior experience. So our activities are going to be either food, so we're going to have lunch. There's going to be a guest speaker session where an industry professional from IBM Quantum is actually coming in. He got his PhD from Duke in quantum information. And then there's also going to be a tournament. So there's going to be a tic-tac-toe tournament with brackets and everything. So if you win that, you get a cool prize. And then there's going to be a t-shirt giveaway and also a Qiskit demo. And then we're also going to have our workshop, which is going to be, I think we're right now thinking about quantum air or quantum workpiece. So.
Yeah. So this QR code is going to be for the registration for this event. And if you pull up, you get a certificate from IBM in quantum computing. And you're going to get a ton of food and a ton of prizes. It's going to be awesome.
And also we have, I believe we have CLE credit. If you call it.
Oh yeah, that's
So,
true too.
Yeah, so be sure to come. Yeah.
Yeah. Tell all of your friends that too.
Yeah.
Okay, so really quickly, before all of you guys leave, make sure you join the group meet. This is going to have all the information with the club,
Yeah.
pretty much always. Quantum Fest registration, this was the same QR code on the previous slide. This is how you register for our Quantum Fest event. Completely beginner friendly. If you're in UNC, you should pull up at least for the free food and the IBM certificate and the CLE credit.
Yeah. It's really important that you do register for this because we're gonna be checking like the head count so we know how much food to order.
Register here. If you go to the Google form, it'll say fill out Google form and the field life form. So if you go to Google form, it'll say it.
Yeah, and then make sure you also follow us on Instagram where we also post updates and pictures. And then we also have our website actually, which I can pull up.
Wait, keep the QR codes. Keep the QR codes on the screen.
Oh shit. Oh my god. Okay. Let me
Just
not
keep the
do
QR
that.
code.
Yeah.
Okay. Yes, and if you really hate us, you can give us feedback.
Yeah.
So, yes.
Thank you guys for coming.
Yeah. Thank you so much.
Yeah.
let me
me
Oh, yeah.
Okay. If you want to join the group, I'll give you the other one then on November 12th.
It's not really useful then.
Yeah.
Oh yeah, of course. 1 second.
Yeah. Okay. I trust that you will join the group.
Okay, I mean, you're right.
Okay. You were.
You're so
Sorry, 1 second.
Okay.
It's loading.
I'm sorry. Like, if you join the group, yeah, I promise you. I got you.
Yep. There they are.
Thank you.
Wait, do you need this for food too, or just the?
Yeah, this should, you can just pull up.
I know, but
Oh,
it's
yeah.
so fun. Wait,
You
do
can't
they
even-
have a band?
You can't even get boba anymore, so they closed the
Yeah,
boba.
yeah. What about
So
then why are people asking for stickers?
you can get a t-shirt.
Eight is a tote bag.
Yeah,
What?
8 is the tote bag, 2 is the t-shirt.
8 is a
Oh.
tote bag, 2 is a t-shirt.
Wait, seriously?
Yeah. Do you want to?